We got two curling stones on an ice rink, and they collide. And let's see, are they the same mass? Nope, stone one is heavier. And they collide dead center. I'm going to assume that this is an elastic collision, because if it isn't, I won't be able to solve it. So looking at it, it doesn't tell me it's elastic, but two pieces of granite hitting into each other, I'm going to assume it's elastic. And I think that there was something about curling in the chapter that talked about it being an elastic collision. And they want to know the velocity of the two stones. Be careful, part A is for stone 2, and part B is for stone 1. And I would have put them reverse that, but just make sure you're always careful of that stuff. All right, so this is number 14, right? And in the writing, I might put this is an elastic collision. Therefore, kinetic energy is also conserved along with momentum. You know, something just to show that I understand the ramifications of it being an elastic collision. So, curling stone 1 and curling stone 2, and beforehand, I'm going to call that momentum 1. And then by during, they're going to be in contact with each other. And I'm going to have equal and opposite impulses. So impulse on 1 caused by 2, impulse on 2 caused by 1. All right? And then afterwards, I'm going to predict that 1 is going to continue forward slightly. So I'm going to give it a small momentum this way. 2, I think, is going to have a larger momentum. I'm going to call that momentum after, shown with that little tick mark, 2, and momentum after, shown with the tick mark, 1. So those are the diagrams. Can't get all 3 in there, but before, during, and after, with all of my momentums, not my velocities, not my other things. Okay, I could add in the masses there if I wanted, things like that. But those vectors have to be labeled as momentums and impulses for credit. All right, because if I look at my rubric, all momentums shown in correction diagram, all impulses shown in correction diagram. So if I don't label them as those, I don't get credit for this. All right? And the nice thing about my impulses is I know they're always come in pairs, they're always equal and opposite. That's what made Newton's third law, right? So, all righty. Any questions about the why before we jump into the how? Yes, sir?
Yeah, on the last one, what's that little dash above the P's mean?
That's called a prime mark. It's commonly used in math to show a different value. A lot of times in momentum and energy, it's to show an after value.
Okay.
Yeah. It's another way of looking. What math are you in?
Calculus.
Okay, when you get to calculus, they'll be used a lot more extensively if you get to calculus.
We've already used that for like
so you've seen it before.
Translate. I just wanted to.
That's great. Yeah, geometric. Yeah, you can show it with showing like similar triangles, things like that. Yeah, but yeah, it just means a different value of P1. All right, so start with the valid physics equation. Let's see. I'm going to start with, I know my momentum's conserved, so my momentum, I can grab it from here. My momentum of the system equals the momentum of the system afterwards. So momentum of the system equals momentum of the system afterwards. I know my kinetic energy of this is going to be conserved. So I could write that also if I wanted to. I should write the definition of kinetic energy and the donut and my equation for momentum. All right, all those from my equation. So let's start with the momentum. So beforehand, from my before diagram, I have momentum 1. Afterwards, I have momentum 1 prime plus momentum 2 prime. And those are taken directly from my diagram, my before and after. That's one reason it's helpful to get those like a force diagram. Get them correct, and then the how follows directly from them. So this would be mass 1 or inertia 1, velocity 1, and that would equal, these should actually, technically I should have vectors on these, sorry about that. And then, huh? No, not as long as you showed, like if one where it was an explosion, if you had them both positive, that's going to mess with you, so, but not, no. Mass of 1 stays the same, velocity of 1 prime, plus mass of 2, velocity of 2 prime. And let's see, what do I know? I know mass, I know the masses, what are they? 21 and 16, and I know V1, for me it's 2.5. Question. 21 kilograms, positive 2.5 meters per second. 21 kilograms, don't know. Don't know. And now I have a problem because I have only one equation, but 2 things I don't know. So I'm kind of stuck. This is where, if it isn't an elastic collision, they didn't give me enough information to solve it. Considering that they think I can solve it, it must be elastic. That's where that conservation of kinetic energy comes in. So, now I'm going to use that the kinetic energy of number 1 has to equal the kinetic energy after of 1 plus the kinetic energy after of 2. That same conservation idea. So 1/2 inertia of 1, speed of 1 squared. 1/2 inertia of 1, speed after, I'm going to put parentheses around that, squared, plus 1/2 inertia of 2, speed of 2 after, squared. Anything I can get rid of to simplify? Any mathematical things I can do to simplify that? No? All right. Let's continue forward then. 1/2, 21 kilograms, 2.5 meters per second squared. I think I'll move that thing. Equals 1/2, 21 kilograms, V1 prime squared plus 1/2, 16 kilograms d2 prime squared. Now, luckily, I have the same. I can't go any farther on the red because I have one equation and two variables, but luckily they're the same two variables that I had when I got stuck in the green. So now I have two equations, same two variables that I don't know. So mathematically I know, yeah, I can solve it. All right? How would you go about solving these two equations with the same two unknowns? Come on, make your algebra teachers proud.
System of equations.
Okay, I could use systems of equations, yeah. Other methods people think of? Personally, the way I think about it is I say, oh, wait a minute, I'm on the first floor, so I'm not in my math class. Oh, so I could use, like, Wolfram. So I'm going to use Wolfram to solve my problems. And links. So I think I will use Wolfram. I like Wolfram more. So 21 times 2.5 equals 21. I'm going to call my V1 D. 21 times, I'm going to call it A, plus 16 times B. So there's my first equation. Is it worth me going through this, or you know what you're doing from this point? Keep going? Okay. And then I'm going to put in my second equation, so I'm going to do comma space to tell it's a new equation. And then I'll put in my 1/2, 0.5 times my 21 times A caret 2 for squared equals 0.5 times 20. Oh, wait a minute. Nope, that's not. Sorry. That's not A. That's 2.5. 0.5 times, now this one is A squared, plus 0.5 times 16 times B squared. So I've got in my two equations. And right, this will all be on that video. And I mean, the trickiest thing I did is convert 1/2 to 0.5 in my head. Right. Oh, it's a circle. So there are my two possible solutions. I'm going to hit approximate form so that I don't have to deal with fractions. And so one solution would be the first one kept going and the second one didn't move, but they hit each other. So I don't think that's possible, because that would mean the first one just literally passed through the second one. Mathematically that might make sense, but it doesn't make sense physically, you know. We can try it though. We can have one person run into another and see if they pass through. Okay. Let me know if you want to do that later. We'll give it a try. So, where we go? No, come on, don't have frozen on. So I'm going to try those. 0.338 for stone 1. And then 2.84 for stone 2. Oops, oh, no, I didn't. What was that, 8.4? Alright, a friend climbs an apple tree and drops an apple from rest to you, standing 3.5 meters below. When you catch the apple, you bring it to rest in this amount of time. And they want to know, what is the speed of the apple just before you caught it? What average force did you exert on the apple to bring it to rest? So this is actually kind of both, really, because part A is very straightforward to do with energy, and then part B, because they told me the time and they wanted a force, right away I think about impulse. Since impulse is force times time, it's combined, it has both of those. So I see both those, I think about impulse. That would mean I would use momentum ideas to do it. So I would say the Y, if I was including one like this on, the evaluation on Wednesday, I'd probably put an energy bar graph for the Y. Yeah, if I had this type. So why don't we attack it with that type? All right, so number 11 here. And so let's see. The initial, it's going to have some PE grav. Remember, if I add that to one side, I have to add it to both. I don't think there's any other energies going on here. So I'm going to have my initial is going to be at the top and just before the catch will be my final in this. Not like when it's finally stopped. Although I could do energy for that, I think it'll be easier to do with momentum. So at the beginning, it had a lot of PE graph. It fell through the air, but they didn't tell me anything about air resistance or like helicopter blades or anything on it, so I'm going to assume that there was no external work done on it when it fell. And then when I get down to the bottom, I'm going to call that a zero potential energy graph. So all of that energy must have gone into the kinetic energy. Oh, that looks like number 2 on those creative tasks that you did. It does look very similar, yeah. Like identical, almost. Any questions on the Y? All right. So I get up a little easy in my Y. I don't have to explain about momentum, but I might add some things in there. You know, if I was like, ooh, it's a test, I have to make sure he understands I know. So my energy bar graph told me the PE at the top, and that was grav PE, has to equal the KE at the bottom. And I would grab my equations from my good old trusty equation sheet. Right? I might even draw myself a little diagram over here. All right. And then I substitute in. And let's see, what information do they tell me? 0.22 kilogram apple. Right? And what's the speed of the apple just before you caught it? Okay, well, 9.81 newtons per kilogram. It went down 3.5 meters. That's going to equal 1/2 the speed squared. Common mistake will be not forgetting to square root your answer before you write it down. How did I get rid of that mass?
It's on common.
Oh, I could have gotten rid of the 1/2 in that previous problem, couldn't I? Because it was in every term. Oh, that would have saved me some typing. So I get 5.8596 meters per second. If I wanted to, I would check that. I don't feel like checking it. When the person's hand is in contact with the apple, there's an impulse down from the apple on the hand. There's an impulse up of the hand on the apple. And I know those are equal and opposite. And it's the impulse that causes the change in momentum. So I'd go back to my equation sheet and know that J equals the change in momentum. And so I could also write, well, I know the inertia doesn't change, but the velocity changes. And that's going to be, I could even go further, V final minus V initial. What is the V final if they catch the apple? 0. So far I haven't had to deal with direction. For make my life easy, I'm going to call down positive. Because remember, energy is just a scalar, so we don't have to worry about, that's why it's speed and height and things like that. But our momentum is a vector here. So, I should probably expand off this time that this is force delta T, right? That's what the definition of impulse is. So now I'm just going to use my extremes here, and I'll have force delta T equals the inertia V final minus V initial. And I'm looking for my force. So I actually don't know that. I know my time, 0.28 seconds. I know my inertia, 0.22 kilograms. I know my V final is 0. My V initial I know is positive 5.8596 meters per second. And I solve for F. I'm going to get a negative value, I hope, because that impulse should be pointing upwards. So let's hope I do. And I do, which is nice.
Where'd you get the 5.5?
What I did in blue. The speed of the apple just before it hits the hand is the velocity of the apple.
Yeah, we have the same thing.
Like values.
It doesn't matter. 8.3.
Do you remember the square root?
Yes.
Okay. Did I forget the 1/2? Did I forget the 1/2? I did, I forgot the 1/2. Good catch, I'm glad you guys are paying attention. Yep, that's what I get now. Yay. Thank goodness for people paying attention on a Monday morning. 8 points. You guys agree.
How can you take out the 1/2 like the 4?
In the previous problem, I took it out because it was in every term. Yeah, we're talking about the previous one. Nope. So this I need to change also. There we go. You know what? And I'll even put it in blue to make it clear. There we go. And so I do get negative 6.51 newtons. And of course I'm going to report that as 6.51 because they just have, my guess is they just want the magnitude.
I think. It might be something else.
Okay. Oh, we skipped over number 1. Oops. So we'll do number 1 next, which I believe is also an energy problem. Right? I love it that people pick the high value problems, even if they're not the hardest. It's always interesting to see. Yeah. But honor students aren't interested in just grades. Alright, so this one I believe is also an energy bar graph one, if I remember correctly. Yeah. Which problem is the hardest? Well, I took out the hardest one. Well, because it had coefficient of friction. We'll bring it back in a couple chapters, in a couple units, but probably any of them that deal with elastic collisions, I would say.
Yeah, 9.
All right, so we've got the two masses initially at rest at the same height. After they release, the large mass falls through a height of h and hits the floor, and the small mass rises through a height of h. Find the two masses just before M2 lands, and okay. Oh, so they want us to leave it in terms. This usually freaks people out because they're like, I want numbers. And then you give them numbers. I don't like math. So you can't win. But we'll leave it in terms of M1 and everything like that. All right. And then we're just verifying it here. So energy bar graphs on this one. I think I'm going to do 2 bar graphs on each one because, since I have 2 different masses, right? But we're going to have PE grav. And I'll do them in blue green. So, on when they start in the middle, blue is going to be mass 1. It has that much potential energy grav. Green will be mass 2. It's going to have that much. Why does the second mass have more PE grav than the first mass when they're sitting at the same height? It has more mass, so therefore it has more weight, therefore it has more gravitational potential energy. And then afterwards, we're going to have, they're both going to be moving, right? Now, if they're connected by a rope, and the rope doesn't go slack, what can we assume about their motion? All right, if if anyone figures that out, let me know. If we get to a part of the problem where we need that fact, and we haven't figured it out, maybe we can put a little more thought into it and some suggestions, okay? But I'll tell you, we're going to hit a point where the fact that they're both moving and there's a tight rope between them tells us something about their motion, and if you haven't gotten it, we'll be stuck. So think about it. Let it percolate in your brain. All right, so before they both have PE graph, there's no external work during. Afterwards, they're both going to be moving. I'm going to say like that for M1, and I'm going to say like that for M2. Anyone figure out the facts yet? Yes, they have to be moving in the same direction. And that's what a pulley does, to change direction. Something else about their motion. And let's see. This one is going to have a bunch of PE grav, but no PE grav for the big one, for M2, because it's just about hitting the ground. So let's see how many I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. So I've got to go up. Where's that? 5 here. It's 5 plus 5 is 10. So my energy is conserved because I got 5 before, and then I've got 5 afterwards. All right? Any luck? Anyone else figure out? If you're running with a friend and you have a tightrope between you, anything true about your motion? Nope. All right. Any questions on this before we move forward? All right. So, I know my energy is conserved. So, let's actually pull it down in its color. So, PE 1 beforehand plus the PE of grav of 2 beforehand, this should be grav, equals KE of 1 plus PE of 2 plus PE afterwards gravitationally of 1. Oops, and this should be KE. Right, and that's right from my graph. Yeah? Alrighty, so mg h1 plus, that should be m1, m2g, it's also at h1, equals 1/2 m1 speed 1 squared plus 1/2 m2 speed 2 squared plus m1g, I'm going to call that h2, just for now. Not h2. h1 prime. So I just substituted it in, right? And I'd probably write above this KE, oh, I looked on the equation sheet. All right. So, let's see. They tell me that those are little h's, right? So I'm going to say from here, I'm going to call this point 0. I'm going to call that initial height little h, and that top height 2h. Okay? Yes, everyone okay with that? Okay. So this would be m1gh plus m2gh equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus m1g 2h. They want me to find V final. Which one of these is going to be V final? V1 or V2? Wait a minute. Oh, I don't know how to solve that thing. Let's see if there's any clues in the question. Find the speed of the masses. So they don't even say which one they want, the speed of mass 1 or the speed of mass 2. Wait a minute. If I'm running and I've got a tight rope between us and the rope stays tight, I have to be running at the same speed. Oh my God, how's that possible? It just hit me. Because if the person in front runs slower, the rope would go slack. And if they ran too fast, they'd pull me off my feet. Wow, I got to try that sometime. I wonder if that's true. I have a big rope. Nah, you guys don't want to try stuff. That's okay. All right, so those, I can get rid of these stupid 1s and 2s then, right? Because they're the same. So, there's lots of stuff I can combine. See what you can figure out to combine. I'm going to combine some stuff. So, see if you can, I'm going to get, yay! Gotta love these, yeah.